Tonight we are going to watch something die, not quickly, not violently, not in the way we think of death, sudden, final, loud, but slowly, over millions, sometimes billions of years. A vast engine of fire and gravity, burning through its last reserves of hydrogen, growing quieter and quieter at its core, even as its outer layers swell into something enormous and strange. A star is dying somewhere in the universe right now. Many stars are, and the way they die, the process, the stages, the things they leave behind, turns out to be one of the most important stories in all of science. Because the death of stars is not a footnote in the history of the universe. It is the mechanism by which the universe builds everything, including you. Before we go further, if you love sitting with the deep questions of the cosmos as much as we do, take a moment to like this video or subscribe. It helps these explorations reach more curious minds. Now, let us begin. To understand how stars die, you first have to understand what a star actually is. A star is a war. Specifically, it is a war between two forces that never stop fighting each other for as long as the star exists. On one side is gravity. Gravity is pulling every atom of the star inward toward the center, trying to collapse the whole enormous thing into a single point. On the other side is the energy produced by nuclear fusion at the star's core. Enormous quantities of heat and light and radiation pressing outward, in every direction, trying to expand the star and push it apart. For most of a star's life, these two forces cancel each other out. Gravity pulls in, fusion pushes out. The star holds its shape. It sits in a kind of perpetual stalemate that can last millions or billions of years, depending on star's size. But the stalemate cannot last forever, because fusion is not free. It requires fuel, and the fuel is hydrogen, which the star is burning through every second of its existence. The fusion process works its way up the periodic table, fusing hydrogen into helium, helium into carbon, carbon into oxygen, until something stops it. That something is iron. Iron is the graveyard element. It is the one element in the universe that cannot be fused further to release energy. Fusing iron requires energy, rather than producing it. So, when enough iron accumulates in the core, the fusion engine that has been holding the star up against gravity for its entire life simply stops, and in that moment, gravity wins. But that ending, iron, silence, collapse, is not where every star finishes. Not all stars reach iron. The path a star takes to its death depends entirely on how much mass it started with. A heavy star dies one way, a lighter star dies another. And a star like our Sun dies in something altogether quieter and stranger. Tonight we are going to follow all of them. But before the death, there must be a birth. Between the stars, filling the vast and apparently lifeless distances of space, there is gas, mostly hydrogen, some helium, trace amounts of everything else. The scattered remains of stars that died long before our Sun was born. This gas is extraordinarily thin. In the emptiest regions of interstellar space, it amounts to barely an atom per cubic centimeter, a vacuum so perfect that no laboratory on Earth has ever been able to reproduce it. But it is there, drifting, cooling, waiting, and in some places, this gas gathers. A shockwave from a distant stellar death can compress a cloud of gas the way a hand compresses a pillow. Gravity does the rest. The cloud begins to collapse inward, very slowly, over millions of years. As it contracts, it heats up, and at the center, the temperature begins to climb. From the cold of deep space, just a few degrees above absolute zero, toward thousands of degrees, and then toward millions. At 10 million degrees, something new becomes possible. Two hydrogen nuclei can approach each other closely enough that the strong nuclear force overcomes the electromagnetic repulsion that would normally keep them apart. The protons fuse, and in that fusion, a tiny amount of mass is converted directly into energy, according to a relationship first written down by Albert Einstein, E equals mc squared. The star has ignited. What was a cold cloud of gas drifting in silence is now a nuclear furnace, held in equilibrium between the inward pull of its own gravity and the outward pressure of the energy being released at its core. This is how all stars begin, how our sun began 4.5 billion years ago, how every star you see tonight began. In a cloud of cold gas, collapsing, heating, crossing the threshold into fire. The Hubble Space Telescope has shown us this process in action. The image known as the Pillars of Creation shows 3 towering columns of gas and dust inside the Eagle Nebula, 7,000 light-years away. Each pillar is several light-years long. At the tips, small dark shapes protrude like fingers from the cloud. Each one is a protostar, a new sun in the making, a war about to begin. For most of its life, a star like our sun burns in a stable and self-regulating way. If the core gets slightly hotter, fusion accelerates, producing more energy, which pushes the outer layers outward. This reduces the pressure on the core, which cools it, which slows the fusion. Equilibrium is restored. If the core gets slightly cooler, gravity compresses the outer layers inward, the core heats, fusion accelerates, the star settles back. This feedback loop keeps a star burning at a steady rate for billions of years. No external control, no monitoring system, just pressure and heat, adjusting each other automatically, holding the star in balance through the patient physics of opposing forces. Our sun does this right now. At this moment, the core of our sun sits at 15 million degrees Celsius. Every second, it converts 600 million tons of hydrogen into helium. 600 million tons every second. And that release of energy, crossing 93 million miles of space, is enough to drive every living system on the surface of this planet. The sun has been doing this for 4.5 billion years. It will continue to do it for another 5 billion. And then, slowly, something will change. Over billions of years, the hydrogen in a star's core is steadily replaced by the helium that fusion produces. The core fills. The fusion rate slows. The core, no longer generating quite as much energy, begins to contract slightly under gravity. That contraction heats the core. The heat ignites a new shell of hydrogen burning just outside. A ring of fusion surrounding the helium interior, burning through fresh hydrogen in the layers above. The energy from this shell pushes outward into the star's outer envelope, and those layers begin to expand. Slowly at first, then dramatically. Over millions of years, the star swells outward, growing hundreds of times larger than it was during its stable life. As it expands, it cools. The surface temperature drops. The star shifts in color from yellow-white toward orange, toward a deep and burning red. The star has become a red giant. When our sun reaches this stage, approximately 5 billion years from now, it will have expanded to perhaps 200 times its current diameter. Its outer edge may reach as far as the orbit of Venus. The oceans of Earth will have boiled away long before that. Life on this planet, if anything still lives here, will be long gone. But back to the star itself. For a few 100 million years, the star burns as a red giant. In its core, the temperature climbs toward 100 million degrees. And at 100 million degrees, something new becomes possible. 3 helium nuclei fuse together to form carbon. The star begins burning its accumulated helium, releasing a new burst of energy, briefly stabilizing again. This is how the elements of the universe are made. The carbon in your body was forged in the core of a red giant, billions of years before the Earth existed. The oxygen in every breath you take was created in stellar fusion. You are, in the most literal sense, made of star stuff. The atoms that make up your hands, your heart, your thoughts, processed through stellar interiors, expelled into space, gathered into clouds, compressed into our solar system, assembled over billions of years into you. The universe did not create you from nothing. It recycled itself into you. For a star like our sun, the death that follows the red giant phase is quiet. As the star exhausts its helium and carbon burning, its outer layers become increasingly unstable. The star begins to pulsate, expanding and contracting over thousands of years, and eventually, the outer envelope is expelled entirely. The star blows off its own surface in a vast, slow exhalation of gas. This expelled shell, lit from within by the hot remnant at its center, is called a planetary nebula. The name is misleading. It has nothing to do with planets. Early astronomers simply thought the glowing rings resembled the disks of planets through their small telescopes. They do not. They are something far stranger, the last breath of a dying star, spreading outward across space in rings and bubbles of glowing gas. Enriching the universe with the carbon and oxygen the star spent its life creating. The Helix Nebula, the Ring Nebula, the Butterfly Nebula. Each one is a stellar exhalation. Each one marks the place where something burned for billions of years and is now slowly dispersing into the dark. And at the center of each nebula, left behind when the outer layers departed, is what remains of the star's core, a white dwarf. A white dwarf is roughly the mass of our Sun, compressed into a sphere the size of Earth. It is not generating energy through fusion. The nuclear fire has gone out. It is simply the hot, dense remnant of a stellar core, cooling slowly over billions of years, like a coal pulled from a fire and left on a stone floor. Its surface at first is tens of thousands of degrees. It glows blue-white with residual heat. But it is not producing new energy. Every photon it emits is a small loss of the heat it inherited from its past. Over billions of years, more billions than the universe has yet existed, a white dwarf will cool toward the temperature of the space around it. Eventually, it will become what astronomers call a black dwarf, a cold, dark, inert sphere of carbon and oxygen, drifting invisible through a universe that has moved on. No black dwarfs exist yet. The universe is not old enough. The cooling takes longer than 13 billion years. But they are coming. In the deep future, in time so vast it has no name we use easily, the space between the galaxies will be populated by billions of them. Cold stones, drifting silently, the memorials of stars. Not all stars die quietly. For stars more than about 8 times the mass of our Sun, the end is an event that makes everything else in astronomy look small. A massive star lives faster. Where our Sun burns for 10 billion years, a star 20 times more massive burns through its hydrogen in a mere 10 million, and then pushes further. It fuses helium into carbon, carbon into neon, neon into oxygen, oxygen into silicon, silicon into iron, and then the war ends. Iron cannot be fused to produce energy. When the core fills with iron, the fusion engine that has been holding the star against gravity simply switches off. And in that moment, gravity wins completely. The collapse happens in less than a second. A core the size of Earth compresses to a sphere roughly 20 kilometers across in the time it takes you to blink. The density it reaches is almost beyond description. A teaspoon of this material would weigh 1 billion tons. Electrons and protons are crushed together into neutrons. The collapse releases more energy in that fraction of a second than our Sun will release, across its entire 10 billion year lifetime. A shockwave tears outward through the collapsing star. It reaches the surface. In hours, the star brightens by a factor of 10 billion. For weeks, a single exploding star can outshine an entire galaxy of hundreds of billions of suns. A supernova. The Crab Nebula in our own Milky Way is the remnant of a supernova observed by Chinese astronomers in the year 1054. They recorded a new star appearing in the sky, visible in daylight for 3 weeks. What they saw was a star dying, 4,000 light-years away. Its light arriving at Earth 1,000 years after the star itself had already ceased to exist. And in the supernovas, in those final violent moments, the rest of the periodic table is filled in. The elements heavier than iron that cannot be made by ordinary stellar fusion. Gold, platinum, uranium, iodine, all of them forged in the extreme conditions of a stellar death. Every gold ring on Earth, every kilogram of uranium in every reactor, every iodine molecule in every thyroid gland. Made in a supernova, scattered across space, gathered into our solar system, incorporated into the rock of early Earth, cycled through geology and ocean and atmosphere, and assembled into the living world around you. The universe is generous with its violence. After the explosion, what is left? If the original star was between about 8 and 20 times the mass of our Sun, the core that remains is a neutron star. A neutron star is 20 kilometers across. It is composed almost entirely of neutrons, packed to a density comparable to an atomic nucleus. Its gravity is so strong that the collapse of a stellar core, from Earth-sized to city-sized, spins it up dramatically, the same way a figure skater spins faster when they pull in their arms. Some neutron stars spin 30 times per second. Some spin 700 times per second, and as they spin, they emit radiation in tight beams from their magnetic poles. If those beams sweep across Earth as the star rotates, we detect a regular pulse of radio waves, repeating with extraordinary precision. These objects are called pulsars. The first pulsar was discovered in 1967 by astronomer Jocelyn Bell Burnell. The signal repeated every 3 seconds with a precision that initially seemed almost too regular to be natural. It was briefly designated LGM-1 for little green men, because the possibility of an artificial signal could not immediately be ruled out. It was not artificial. It was a neutron star, spinning in the dark, sweeping a beam of radiation across the cosmos with the regularity of a clock. And if the original star was more than about 25 times the mass of our Sun, if the core left behind is too massive to be held up, even as a neutron star, then gravity wins completely. The core continues to collapse, past neutron density, into a singularity, a point of infinite compression, wrapped in an event horizon from which nothing, not matter, not light, not information, can escape. A black hole. The star that lived as a burning, visible, luminous thing for millions of years has ended as an object that cannot be seen. It has become an absence, a place where gravity has finally, permanently, had the last word. But the story does not end with destruction. The gas expelled by dying stars does not drift away into permanent emptiness. It mixes with the interstellar medium. It enriches it. Every generation of stars that forms from this gas contains more heavy elements than the generation before, because each generation of dying stars has added its processed material back into the mix. The first stars that formed after the Big Bang contained almost nothing but hydrogen and helium. There was nothing else. Those first stars burned hard and fast, and when they died, they seeded the universe with carbon, oxygen, nitrogen, the building blocks of everything that came after. Later generations of stars inherited these enriched clouds. They formed solar systems with rocky planets. Planets where carbon chemistry could become complex, where molecules could become self-replicating, where self-replicating molecules could become something stranger still. We are what the universe made when it finally had enough heavy elements to work with. We are the descendants of supernovas. Every atom in your body heavier than hydrogen was processed in a stellar interior, expelled into space, gathered into a cloud, condensed into our Sun, and the disk of material that became our solar system, incorporated into the rock of early Earth, cycled through ocean and atmosphere and geology, and eventually assembled into you. Stars had to die so that you could exist. This is not a metaphor, it is chemistry. The night sky above you contains billions of stars. Each one is a story, a long, slow burning story of gravity and light and time. Each one was born in a cloud of cold gas, found its balance, burned for millions or billions of years, and will one day end in the way its mass determines, quietly as a white dwarf or violently as a supernova. or silently, as a black hole, and when they end, they give back. They return what they built to the space around them, enriched and refined, ready to be gathered into the next generation of stars and planets and possibilities. The universe is not squandering its matter. It is investing it, slowly, patiently, over timescales that make all of human history look like a single heartbeat. Tonight, as you drift towards sleep, imagine it. The dark spaces between the stars are not empty. They are full of the remnants of stars that died before our sun was born. Cold clouds of hydrogen and dust, drifting toward the next slow collapse. The beginnings of the next generation, waiting quietly in the dark. And somewhere, billions of years from now, a star will form from a cloud that contains the atoms that were once part of you. The carbon and the oxygen and the calcium that makes up your body right now will cycle back into the universe when you are gone, into the air, into the soil, into the ocean, into the slow drift of interstellar space, and eventually, perhaps, into a new star. You are temporary, but you are not lost. The universe does not waste anything. Good night. If tonight gave you a new way of seeing the stars, a like or a subscribe would mean a great deal. It helps these explorations reach more curious minds like yours. Until next time, keep looking up.